All right, we're going to start learning about right triangles and trigonometric properties. But first we're going to learn about the geometric mean. So our first lesson today, our content standards, proof theorems about triangles, and use congruence and similarity criteria for triangles. Our mathematical practices in our assignment today are 7 and 3. Previously, you've used proportional relationships of corresponding angle bisectors, altitudes, and medians of similar triangles. Now we're going to find the geometric mean between two numbers and solve problems involving relationships between parts of a right triangle and the altitude of its hypotenuse. Doesn't that sound awesome? Well, let's see what that means. First of all, we have one new vocabulary word, geometric mean. Now, when the means of a proportion are the same number, that number is called the geometric mean of the extremes. The geometric mean between two numbers is the positive square root of their product. So notice that these are the same. If A is equal to 9 and B is 4, then 6 is equal to the square root of 9 times 4. So let's find the geometric mean between 2 and 50. So if we let x represent the geometric mean, remember these are the means and these are the extremes, so we're going to set the extremes as 2 and 50. We have x squared using our cross products is equal to 100. Take the square root of both sides, so x is equal to 10. So the geometric mean is 10. So let's try this out on one of our own. Pause the video and work this problem, then come back and check your answer. So did you get 6? If you set up your problem, your proportion 3 over x equals x over 12, you're going to get x squared is equal to 36. So the square root of both sides, x is equal to 6. Very good. So in a right triangle, an altitude, so here's an altitude. It's drawn from the vertex of the right angle, notice here, vertex of the right angle, to the hypotenuse. Hypotenuse is the side opposite the right angle, and it forms two additional right triangles. Both of those are right. So these right triangles share a special relationship, and that's what we're talking about in Theorem 8.1. If the altitude is drawn to the hypotenuse of a right triangle, so we've drawn an altitude from the vertex of the right angle to the hypotenuse, then the two triangles formed are similar to the original triangle and to each other. So let's identify similar right triangles. And there's a little trick to this. You might want to take this down in your notes. So when we're trying to write a similarity statement, first we have to identify the triangles. So we're going to separate the triangles into two triangles. So this along this altitude, so we've got a triangle on the left and one on the right. And then we're going to sketch the three triangles. We're going to reorient the smaller ones so that they correspond to the original triangle. So we're going to have all the right angles in the same position. That way we can see that they are similar. So here is our similarity statement. EFG is similar to FHG, which is similar to EHF. So when you redraw them and reorient them, it helps you determine how to name the triangles, because these have to be in the right order. Okay, time for you to check your progress. So pause for a moment and then come back and check your answer. Okay, did you get C? So once you separated into two triangles and then reoriented them so all the right angles are in the same position, you should have gotten triangle LMN is similar to triangle LOM, which is similar to triangle MON. And this, well, you can find in your textbook on page 538, but it's explaining more about the similarity. By definition of similar polygons, you can write the following proportions. That's what's inside the circles. The circled relationships involve geometric means. And that leads to this theorem. actually two theorems. We've got the geometric mean altitude theorem and the geometric mean leg theorem. So why don't you pause for a moment and write some notes about these theorems and then come back and we'll actually start working with them. Okay, first of all, we're going to use the geometric mean with right triangles. So I want you to make a sketch of this triangle because on the next slide it's going to vanish and you're going to want this information to refer back to. So pause for a moment and sketch this in your notes and then go on and we'll work the problem together. Okay, so first of all, E is the altitude, it's the measure of the altitude, so it's the square root of Jm times ml. So pause for a moment and go back and look at your sketch. See that E is equal to the square root of Jm times ml. Then we're going to substitute the numbers in. Jm is 6 and ml is 24. So 6 times 24 is 144 and the square root of 144 is 12. So that's the geometric mean altitude theorem in use. Now they want us to find the measurement of leg D. So looking back, D is equal to the square root of Jm times JL. Now Jm is 6 and JL, if you notice, is 6 plus 24. So 6 times 30 is 180. Or if you take the square root of it using a calculator, it's approximately equal to 13.4. So now let's find the measure of C. C is the geometric mean of ML. So the C is equal to the square root of ML times JL, the measure of the segment adjacent to KL. That's the square root of 24 times 24 plus 6. So that's the square root of 720, or about 26.8. So we've got an exact for E because it was the square root of 144, but these other two are approximations. All right, time for you to check your progress. So pause for a moment, then come back and work the problem and check your answer. Did you get 17.9? You're trying to find E to the nearest tenth, so E is equal to the square root of 16 plus, or times 4 plus 16, which is the square root of 320, which is approximately equal to 17.9. Now you can also use a geometric mean to measure height indirectly. So pause for a moment and read through this problem, and then we'll go on and work it. So first of all, you need to draw a diagram of one of the right angles formed. It might be helpful if you were to sketch this diagram in your notes so that as we go through and work the problem, you can see where we're getting the numbers. We're letting yx be the altitude drawn. So yx is equal to the square root of wx times xz. We put the numbers in instead. Notice to go from this step to this one, we simply had to square both sides. Then we divide both sides by 7.25, so xz is approximately equal to 25.14. Now the length of the long rod would be 7 and 25 hundredths plus 25 and 14 hundredths, or about 32 and 39 hundredths inches long. Time for you to check your progress. Oh, we're going to find the length of the aircraft to the nearest foot. So pause and then come back and check your answer. Did you get 231.3? Well, I tell you what, if you didn't, tomorrow in class, why don't you ask me to work this one for you? And I will put it on the board. The first time I quickly worked at it, I got C, and I can see where you got C, but I also see where you went wrong. So I can explain that one to you tomorrow. Very good. Time for you now to start working on the assignment. Good luck, everyone.